Today we'll be studying Chapter 12, Psychometric-Closed System Analysis with problem 12-3-1. We consider a 100 meter cube of moist air at 100 kPa pressure, 35 degrees Celsius, and 65% of relative humidity. We need to calculate the amount of water vapor condensed if the mixture is cooled to 10 degrees Celsius in a constant pressure process. We also need to calculate the heat transfer Q, and we have a what-if scenario. What will the heat transfer be if the mixture were cooled to 15 degrees Celsius in a constant pressure process? So, in order to start with our process, we need to log in thermofluids.net. We go to TESTapps, we follow the HVAC psychometric, and we go to HVAC TESTapps. And here we see that there is state 1 and moist air, so we can start inputting our values. We know that P1 is 100 kPa, the relative humidity is 65, the volume is 100, and the temperature is 35 degrees Celsius. Calculated, we get all the values, and we can continue to state 2, which is constant pressure process. So P2 is equal to P1, the relative humidity goes up to 100% saturated, and the temperature goes to 10 degrees Celsius. We see that we're missing some values, but we know that in these systems the mass of air is going to remain constant throughout the process, so we can make this equal to the mass of air in state 1 to find the volume and the remaining values. We can continue to state 3, and we know it's equal to P1, relative humidity is also 100%. We continue the mass, and in order to find the difference between state 2 and state 3, we found the H value, the enthalpy value. In order to find the enthalpy value, we have in the PC model the equation where we use the specific internal energy plus the pressure times the specific volume at the saturated temperature, which can be found in table E2. We have the temperature is 10 degrees, so we find the specific volume to be 0.001 and the specific internal energy to be 42. Inputting that into the equation, we find that H3 is 42.1. We found the states, we go to graphics panel, we make sure we have state 1, state 2, and state 3, makes sense, and we can go to the IO panel in order to calculate the amount of water condensed in the process. So we have the formula that it is equal to the amount of air, to the mass of air in state 1, times omega 1 minus omega 2. We find, so we have a problem right there, but we find the mass to be 1.73 kilograms. We can do the same to find the bundle of work, which will be the pressure times the difference in volume. So we have volume 2 minus volume 1. The boundary work, we find it to be negative 1037.9 kilojoules. If we go to the process funnel and we make sure that we input the states and the boundary work found, which was 1037.9 kilojoules, we can calculate the heat transfer value, which is negative 7,224. For the what-if scenario, we need to make sure that temperature changes to 15 degrees Celsius. So I already took the liberty to input all the values in order to don't waste time. State 1, we know that the state 1 remains the same. State 2, we change, everything remains the same, but T2, which is changed to 15, and for state 3 is the same, but we need to find the values for the specific volume and specific energy at 15 in table B2, which is 0.001 0.01, sorry, and 62.99. We find that the value for H3 at 15 degrees is 63.09, and we make sure the graph makes sense. Here it is, saturated state 2 and 3, and in putting the same equations in the IO panel, we find that the condensed amount of water in the system is 1.39 kilograms, and the boundary work for this is negative 835 kilojoules. In the process panel, we put in the same states and the boundary work just found, we get that the heat transfer in this case is negative 5,820. So we can conclude with this problem and the difference in temperature that if there is a bigger difference in temperature in the process, there is going to be a bigger amount of boundary work and a bigger amount of heat transfer in the systems, as we can see how the system that was cooled to 10 degrees Celsius has a boundary work of negative 1,000 and a heat transfer of negative 7,000. With respect to 15 degrees Celsius, which goes to the boundary work of negative 800 kilojoules and heat transfer to be negative 5,800 kilojoules. Thank you so much for your time and attention.